let's take some of this green powder and put it in a test tube here. So we can see that green powder. Then so what's happened to the powder? We started off with that green powder, and now we've got what color powder?
Black.
Right, we got black powder. So when we heat things up, what usually happens? What happens when we heat things? So, anyone got any sort of suggestion of when we add heat to a material, what will happen to that material? So we used this blowtorch. It works like a Bunsen burner, and we can add heat to a substance. So we've added some heat to this green substance, which we are currently is unknown substance to us. Well, when we heat something, what's going to happen is the temperature of that material is going to rise. And when the material starts getting hot, it can burn. Did this burn?
Yeah, it did, yeah.
Right, you think it burnt. That's interesting. Because usually when something goes black, it burns. It's a sign of it burning. So let's do another experiment with our copper powder. So what happened there when we put the copper powder into the flame? The powder into the flame. What did we see?
It just burns it, so it did.
Yep, it was burning it. And this flame's quite hot, and so it gave that sort of very quite a white colour. So let's take some of the black powder that I made a bit earlier and do the same thing. Let's tip the black powder into there so it's easier to get hold of. So that's my black powder. What do we notice is happening?
It's heating at higher temperature. It's
Yeah.
more flammable.
So once again, it burnt. And notice that it looked very similar to when we heated it up the first time. So let's take my test tube with some of that black powder in there and add a chemical to it. So I added this chemical here. And what can we say has happened? Has it dissolved?
Kind of, yeah.
Yeah, we could say it's dissolved. I suspect if I left it around for a while, the powder would start dropping out of the solution, but it's reasonably well mixed there. Well, let's go and take some of the green powder again. There's a green powder there. Let's add the same chemical again to it. Can we see what's happened?
It's kind of dissolving it.
Did you see the bubbles as well?
Yeah.
So we have got a gas has been evolved by mixing this together. You can see more of the gas has been evolved there. What else is happening? Can we see anything else?
Not sure. Changes color a bit.
It's changing color, isn't it?
Mhm.
And so it was a green powder originally. Oh, that's a bit difficult to see. Let's go and put this onto there. And now we started off with that green powder, and now
Yeah.
it's a bluey color there.
Mhm.
Let's do another experiment. Right. Let's take our blue solution. So we're boiling off the water there. You might be able to see the steam that's coming from the top of the test tube. Oh, let's put it against the dark background. That makes it look a bit more visible.
Yeah.
Now, water is quite interesting. It needs a lot of energy to cause it to evaporate. It's got quite a high specific heat capacity. So we started off with about 4 centimeters cubed of liquid. Notice the liquid's getting darker because it's becoming more concentrated. So when we boil off the water, we produce concentrate. And if we want to make orange juice, concentrated orange juice, we just need to squash some oranges, take out the liquid, And then if we remove the water, we will end up with a sort of a syrup of the sugars and the colours and the things that will boil at higher than 100 degrees as our syrup, which then we can dilute whenever we want to drink. Let's see, darker still. Notice it's got a bit darker.
Yeah.
Let's see what happens next. Let's see. See, we've got a sort of a yellow solution. So let's turn that off. So we've taken a green powder, we've heated it up, and it can turn black. When we add this liquid here to it, it goes blue, and then when we heat it up, it goes yellow. And so one of the ways in which we can tell a chemical reaction has gone on is because we've got a color change. And so we have seen a number of color changes. Now I am going to, wow, it's quite hot. Oh, well, yeah, let's put it in a glass beaker. So I will leave that there. And we've also seen another example of how we can tell that a chemical reaction has occurred is we saw a gas being produced. So let's go and look at another example of a chemical reaction. So I've taken this white powder and I am going to grab this. Does anyone know what this is?
No.
Oh, well, that's a bit easier to see.
It's a thermometer, isn't it?
Yep, this is a thermometer. And if we put the thermometer in our powder there, we can see that the temperature is about 24 degrees. Yeah?
Yeah.
Brilliant. Right. So let's take another glass beaker and put some water in it. Let's put this here. And we've got our thermometer in the water, and this water has come from the tap and is around 22 degrees or so.
Yeah.
So let's take the white powder and the water from the tap and mix them together. Now, you're not supposed to stir things with a thermometer. What is the temperature now?
60.
Yeah, it's getting on. It's risen.
Yeah.
So why has this got hotter? See, it's 66 degrees now. Let's give it a bit more of a stir. So we took some water and a powder, both at just around 20 to 25 degrees. And by mixing the powder and the water together, we have got a solution, and it's increased in temperature. You might just be able to see some of the steam coming from it, because water, when it gets to sort of 70 odd degrees, is going to start steaming. And this beaker feels very hot to the touch, as you would expect. 70 degrees is quite a high temperature against our skin. So this is another example of when a chemical reaction takes place.
Yeah.
We get temperature being given off. So now this solution here is quite an interesting solution, and I am going to grab a test tube. I think, no, we'll grab a beaker. That's it here. And so let's take some of this again and pour a little into there. And so I've got a sort of a pinky coloured solution there.
Yeah.
Let's dilute it a bit more. A bit more. That looks quite nice. So now it's almost colourless. Let's add some of this to it. Now, let's take some of this, that hot solution I made earlier, add some water to it. What happened there? What has changed?
The color.
The colour has changed. I've added a bit more of my special chemical there. And Now we've got a lot darker. So what happened there?
It kept changing color.
It kept changing color. And if we take a pink color solution and mix it with a colorless solution, it usually stays pink. But in this case, the pink is disappearing.
Yeah.
Why is that?
Chemical reaction.
We've got a chemical reaction. So this isn't mixing of colors. This is something else. And does anyone know what sorts of chemicals can change color depending on the chemical reaction that goes on? Oh, it's all pink. Right, let's put this out of the way. No idea. Right. Let's take another solution. Let's wash this out. So I've gone and put a coloured chemical into there. And it's a sort of a reddy colour. What's happened now?
Turning dark blue.
Yeah, it's changed colour into... Oh, there we are. Now we can see it.
Hmm.
It's almost a purple.
Yeah.
And now it's... what colour is it gone now?
Uh, Goldish.
Yeah, a golden colour. Now it's a
Red color.
red colour. And now purple again.
Yeah.
Has any of you ever seen these sort of dyes like this that can change colour?
Uh, Not really, no.
No? Oh, right, okay. You've not seen very many experiments. So these are a special set of dyes that change colour depending on whether they're in acid. So this bottle, it has got some sulfuric acid in there. It's a dark colour because it's sulfuric acid from a drain cleaner. So they've added a dye to it to make it less likely that someone will think it's water and drink it. So that's what that is there. This is sulfuric acid, which is found in some drain cleaners.
Mhm.
Sulfuric acid is, of course, another name for battery acid.
Yeah.
Now, at the beginning, oh, well, I took some of the white powder out of this, and this is caustic soda. This is another drain cleaner, but this is a totally different chemical to the sulfuric acid. This is sodium hydroxide, which is not an acid, it's actually an alkali. And so when I take this special dye that I put in there, this is bicarbonate indicator. It's an indicator dye. And as you notice, it has three colors to it. So it has that sort of red. And then when I take my alkalite, that's sodium hydroxide, and drop it in, you see now it goes to a yellow. And then it will go to this purple color.
Yeah.
Now, I've also been using this acid, and this acid is acetic acid or ethanoic acid. You will know it as vinegar. And this acid is not so strong, so I can easily take the indicator back to its yellow state. But adding more of this doesn't really make it any darker, really. So we need to use a strong acid, the sulfuric acid, because the vinegar is a weak acid. And by taking our strong acid there, when we add that to it, we send our indicator straight to this reddy color.
Yeah.
So that's another indicator there. Now, of course, we also looked at this indicator here. Sometimes this is described as the red wine experiment, where you take two colored solutions, one which is going to be acid, which is going to contain the dye, and the other is an alkaline. And when we mix them together, so let's take some of the alkali and put it in there. Then let's grab a bit of water to dilute it a bit. Then if we take that dye and add it, oops, it's not alkaline enough. Let's add some extra. To there. Let's give it a swirl. And now that is colourless there. And now it's gone slightly pink. Let's add a bit more across there. Then we can take that out of the way. Oops. Let's take pink there. Then let's take this one, add in the sodium hydroxide. Let's give it a swirl. Now it should go colourless. It went colourless before. There we are. Now we've got the colour out of it.
Yes.
So this is phenolphthalein, which goes from a colourless solution to a bright pink. It's quite a useful indicator because it allows us to tell whether something is acid or alkaline. It gives a very clear change, unlike the bicarbonate indicator that gives this quite a slow change going from that sort of red colour to the orange to the yellow and then finally across to that dark purple there. So let's put this out of the way. Let's look at another one. So let's take our beaker there and find the next. So I'm taking this one here. And so there is an orangey yellow solution. Let's put the lid on this. So we've got that. Let's add a bit of acid to it and see what happens. Let's add a bit of water to it to make it a bit clearer. That. And there we have our color change. Let's change it back. I'm just grabbing a beaker, pushing it out a bit. There. Some acid. Now it has changed.
Yep.
And what is really nice about these is you can change them forward and back quite happily. That out of the way. So. So indicators are used to tell when something is acid or alkali. And so if we want to find out the strength of an acid, we can use one of these indicators and we can use that in a titration, which we will look at sometime next in September. So we've got these lovely color change chemicals there. So let's go and look at some other chemicals again. So here is that green chemical at the beginning that we looked at. Now, I would have expected you to know what this green powder is because it is quite a special substance. It is called malachite. And that is a green rock that you can dig out of the ground. And it has been used for thousands of years. This green color you will see in Egyptian temples. because this green malachite was used as cosmetics, the eyeliner, the eyeshadow that the Egyptians used. One of these was the green. This was the green that they used because we actually have an Egyptian cosmetic book, and it told us how they made their different cosmetics so that we know for certain what the different ones are. Now, the chemical name of this is copper carbonate. And when we take carbonates and add them to acids, what we get is an interesting change. Let's take this acid. I'm using hydrochloric acid now, which some of you will know is the acid in our stomachs. Now let's see that we can. I presume you can see the bubbles coming from it.
Yeah.
Let's add a bit more. And you possibly notice that there's been a slight color change from there. It's not as green, it's more a greeny yellow.
Yeah.
Let's go and take that substance from and now it's going a nice bluey color. Now we've got a blue color here. It's quite a deep blue because I've taken my copper carbonate and I've added the sodium hydroxide to that, and that gives this dark blue of copper hydroxide. So copper is quite an interesting material in that when it's a carbonate, it's a green color. When we react it with some sodium hydroxide, it becomes this dark blue of copper hydroxide. When we heat it up, the copper oxide and the copper carbonate, we formed black copper oxide. And we can also form copper sulfate. You might be able to just see slight blue crystals that have grown on the side of the test tube there to show that we have produced those distinct blue copper sulfate crystals. Let's go and add some water to this. And we did see the blue solution for a while before it began to break down to form the white anhydrous copper sulfate. And there you can see this sort of white emulsion there. So dump that out of the way and that out of the way there. So let's take another solution. Oh yeah, this screen's in the exact right position for that camera. So let's take the lid off this and do some experiments with this. Now, let's take some of the sodium hydroxide to this. And it's changed colour. And it's gone this sort of purpley blue colour. Let's add some of the acetic acid to it. Is it going to be stronger? And there we can see it's gone a greeny yellow. But when I mix it again, it goes back to that blue color. So that obviously I didn't add enough of the acetic acid. Well, let's take some of this hydrochloric acid and add it to it. And now we see another color change. Notice the yellow's reappeared. Let's go. And now we've got it fully yellow. Let's add a bit more there. And now we've got a red there. Can you see what's in the test tube?
Piece of paper.
It's a piece of paper. Why do you think there's a piece of paper in there?
Not sure.
Right. Well. So I have got this little book of papers, and they're all a nice yellow color. And if I go and look on the label there, it's got universal indicator paper. And I had put that piece of universal indicator paper in our test tube there to dissolve some of the coloured indicator dye of the universal indicator. And depending on the pH, i.e. how acidic or alkaline it is, it will give these different colours. And we've seen that this must be that sort of pH 3, pH 2 there. We saw it gave those sort of yellowy greens as it went through the pHs. And then we saw these darker blues there. So let's grab our spotting tile there. You might be able to see what's happening to the paper. My hands have now got acid residue on them, as you can expect from me handling these pots of acid there. And so there I've got that paper. Let's go and take some hydrochloric acid, dump it on there, and notice it's gone that dark reddy color. Then let's take, I'm sure this is the sodium hydroxide, add that to this one. And we've gone that dark color there. Let's take some of the vinegar, our acetic or ethanoic acid. Add it to that one. And that's gone a nice yellow color, yellowy orange. Let's take some sulfuric acid there. Add that to this one. Once again, it's gone that dark color. Yeah. Let's find. Yeah. This is ammonia. I don't usually get the ammonia out because it stinks, but since I'm the only one that's going to smell it, which is really nice for you, I'm going to pull it out. Let's go and get some more of these. Lots of chemical papers that talk about using ammonia from sort of the 17th, 18th, 19th century, talked about doing the experiments on a windy day because that was a good way of avoiding the smell of the ammonia. This has become quite weak. When I worked in a chemistry lab, I would translate the German papers into English for the laboratory at one stage because I knew a bit more German than they did. And Germany used to be a very strong place of where they studied a lot of chemistry, and there were a lot of very good chemists, and a lot of very interesting papers are only in German, and so you translate them, and you would look out for lustiger Tag and that sort of thing, and that told you that it wasn't a good idea to breathe in any of the fumes from those experiments because someone else had done it for us, which was very nice of them. So we knew that. Let's go and mix this up a bit more. Let's see what happens to these papers, see if they will go a darker colour. There we are, that has gone a darker colour there. And so we've got another colour there. Let's dump this out of the way. And then let's get some water. Let's add some water to this. Oops. And then we've got some more colours appearing there. So this paper shows multiple colours, and so you can use it to tell the relative acidity or alkalinity of a substance, so we can see whether they are strong acids or whether they are weak acids. So that orange there, the yellow there, and even weaker acid, that light green there, which is more or less neutral, the reds, the very strong acids, and these sort of dark purpley greens and blues showing the alkalis as they're getting stronger and stronger. So there are lots of different indicators. We've just looked at the phenolphthalein that goes from bright pink to colourless. The pH paper there, we've looked at the bicarbonate, which gives three colours. And we looked at the blue one that went from blue to yellow. That's the bromothymol blue. And so that changes colour there. There's also this one here, which I haven't shown you. This is litmus, and litmus comes from lichen. And so that white growth that you see on roofs of buildings and on trees, particularly in areas where the air is a bit cleaner. So where I am in London, you don't see so much of where it is where I am. But if you travel a bit further out to the outskirts of London, you start seeing more and more of this lichen. And that's where the litmus comes from. Another one that you can use is methyl orange. That's in the chemistry syllabus, as well as the litmus and the phenolphthalein. But there are hundreds of different indicators, and the indicators are all around us. Another example of an indicator is beetroot. You probably know that some beetroots are yellow and some beetroots are red. And if you take red beetroot juice and add some alkaline to it, you will notice that the red beetroot juice will go to yellow. And if you add acid to the beetroot juice, it will go to the red. So beetroot is another indicator. And so that shows us that the yellow beetroot is the same dye as the red beetroot. So the colors are from the same chemical, and it's just the different acidity or alkalinity will show whether it's going to be a red beetroot or a yellow beetroot. Another example of these types of indicators are red cabbage. Cabbages can be green or red. And sometimes if you make red cabbage up and add some soap to the pan, which was that sort of reddy purple color, you'll notice that the liquid goes a green or even a purple. And red cabbage juice, as you add alkali to it, it will go to a green color. And if you add some strong alkali to it, like caustic soda, it will go a bluey, purpley color to show how that color can change. If you take flower petals and crush the dyes out of them and test them again with an acid, it's usually best to use a strong acid and a strong alkali. You'll generally find it will produce two different colors. So indicators are all around us, and nature uses indicators to change the colors of flowers. What's it? It's a hydrangea. If you put lime around it, it will go one color. And if you start putting old tea bags around the plant, it will go to this pink, because sometimes you'll see pink versions and sometimes you'll find blue. And it will change color depending on the soil, which is quite an interesting color change there. Now, so do you have any questions? No questions?
No.
Does a course lead to an exam?
Yes, so I've been teaching the IGCSE Edexcel chemistry for 20 years, maybe a bit more than 20 years, 22 years now. And so we're going to be covering that. Today I wanted to do a number of experiments. I want to do as many experiments on camera as possible because it's a bit more interesting to see the experiments being done live rather than watching some carefully curated video. But the course is mainly a theoretical course, like all science courses at GCSE level. There's not very many practicals. So there's going to be practical bits, but there's also going to be lots of written things and looking at the periodic table, which they want you to know about, and the different elements, compounds, mixtures. There's organic chemistry. I've got a modeling set that we can look at the structures of these different chemicals in 3 dimensions, which makes it so much easier than seeing it in 2 dimensions. But yes, is that it's going to be a 2-year course, just like most GCSEs. So that's 5 terms. I hope to have all the content done by within sort of 4 terms that autumn, because usually my students, I get them to start doing revision after Christmas and then start doing past papers after half term. The syllabus is quite narrow, so they keep asking the same questions in the exams. So if you've done all the past papers, you have an enormous advantage because the questions in the exam can be very familiar. Some of my students this year said, oh, there was all these questions that I'd already answered. It was so easy. So that's really something I want to focus on towards the end, so that you get used to getting the language that they want, because they're not really marking you on your scientific knowledge. They want you to be able to regurgitate set statements, and as long as you make those, then you're going to get the mark. But we are going to be looking at all sorts of interesting bits of chemistry as well, so that it will help you if you go into a career in chemistry, going on into A levels and then into degrees if you so wish. So that's the plan. So there's going to be an assignment each week, and there'll be all sorts of quizzes and other activities, as well as just listening and watching me. So I hope that gives you all you need to know. So
yeah.
right, I suppose we should finish now. And but yeah, if you've got any more questions, just get in touch and I can answer them. And so that will be no problem. So yeah.